All right, so today we're going to start talking about our kind of core program execution, specifically stack memory today. So, yeah, LT5 doesn't require a file. So, let's talk about the lecture objective today, which is kind of loosely related to today's lecture content. I didn't quite know where to put this one, so I just put it on this lecture. It's kind of loosely related, though. So for this objective, we want to write greater circle distance, a method that's going to find the distance between any 2 points on the planet. So given 2 points by their latitude and longitude in lists of doubles, so a list of doubles of size 2, and you can assume, you don't have to do input validation, you can assume that the inputs have exactly two elements, the first element representing the latitude, second element representing the longitude of any 2 locations on Earth. So we have these 2 locations on Earth, and we want to find their greater circle distance, which is the distance between those points, which is as the crow flies, as the term goes, but the shortest path between those 2 points on Earth following the curvature of the Earth. So you can't bore through the Earth's crust to get between these 2 points. We have to travel along the surface, so we're trying to find a chord on a sphere between these 2 points. That's what we're trying to find. So, which can be a daunting task. That seems like quite a bit to handle for a course like this. It does imply that you understand a lot of math, a lot of geometry, and a lot of trigonometry. But that's not what I'm asking you to do on this lecture question. So I give this link in the documentation. I give this link related to this question that helps you find this greater circle distance, and it gives you the JavaScript code to solve this question right here. Oh, not that top part. Right here. This code right here will solve exactly what we're asking for. So this is not a question in computing the greater circle distance. This is a question in converting code in one language to code in another language. Can you take this JavaScript code and convert it into Scala code? That's what this question is all about. So don't get scared by the sines and cosines if you don't remember all your trigonometry. If you don't want to question what's the Haversine formula and how it's used and how all the trig identities are used, no problem. Take this code in JavaScript, convert it to code in Scala. So another thing this site gives us is this nice tool right here that takes 2 points, they're lat long, and gives us the distance between those 2 points. So this is what you want to use to generate your test cases. So if we take this tool and we add, which it gives you the north and west, east, south, the default gives you those types of lat long, but you can just do like 30.5 and it'll handle that as well. So if we make up some test cases here, uh, 60.4, I don't know, I'm just making up numbers, and 3.43. This will give me the distance between those 2 points in kilometers to the nearest kilometer, and I have my test case. Now I write this as a test case, I expect this output, and I'm good for one test case. We want to add some negatives, make sure we're handling negatives fine, and play around with these. When you do this, when you generate your test cases, make sure, a couple of things, make sure you're within the bounds of acceptable lat longs. The latitude has to be within -90 and 90. The longitude has to be between -180 and 180. If you're outside of those bounds, your test cases are going to be broken. So make sure you're within those bounds, or you're going to have broken test cases, and it's going to say you're not going to get this value from your output. This value is going to be different than the value that you compute using this equation. Because this calculator, I had to dig into the code and figure this out because it was driving me nuts, but this calculator actually doesn't use this code exactly. It does some input sanitation to make sure it's within bounds. So be careful about that. And 2, this distance is within 1 kilometer. So when you're comparing your doubles and checking with an epsilon, make sure your epsilon is a reasonable value. 1 kilometer is a good epsilon here. So we always want to be carefully choosing our epsilon to be appropriate for our problem domain. And for this problem, since our test cases are generated to the nearest kilometer, we can't have our testing checking with more accuracy than that. We can't use our 0.0001 as our epsilon anymore when comparing doubles in our test cases. We have to do more like 1.0 for our epsilon. So 2 things to be careful of with this one. Other than that, convert this to Scala, use this to generate your test cases, and you're good to go. So this site, you should be utilizing this this extensively to work on this lecture objective, soon to be called lecture tasks. Oh, where is it? All right. So this site, go to this link. That's going to help you out working on this this lecture question. Is that distance along a sphere or straight line distance? It's a chord on a sphere. Using that equation. And that site has more resources, and you can look up greater circle distance and get more information about it if you're curious. But that's not required. Just translate that JavaScript to Scala. Generate your test cases using that online tool. And that's generating our test cases. Last time we generated them by hand and then had them test our code. No matter where you generate them, you want some absolute truth, something that you know is correct. You know your test cases are correct. In that tool, we're going to assume that that's correct because I'm telling you it's correct. I used it to generate my test cases, and then I tested my code against it, verified everything, looked through their code and everything, made sure it was all on the up and up. That tool is correct. Use that to generate your test cases. All right, in JSON. JSON's actually, I see a lot of chat about it right now. JSON's one of those topics I actually cut from this course. We're going to talk about it again in 116 because it's much more difficult to do in a strongly typed language than a loosely typed language. It's one of those things I cut it out so we have more room for everything else that I want to talk about. But JSON is a big topic. It's very difficult to do, more difficult than JavaScript and Python anyway, to do in a strongly typed language like Scala. For example, what data structure do you use? Like if you're parsing a JSON object, use a map of string, that'll work, but what's the value? A map of string to what? Since JSON allows mixed types and Scala does not, that jams us up a bit. All right, so let's get into this. So we want to start talking about what happens when our program executes, and we're going to start tracing through program execution line by line and seeing what actually happens when it's ran. Before we can talk about that, I want to talk about interpretation versus compilation. Just really quick, a couple of slides. Interpretation, when a code is interpreted, this is what happened in JavaScript and Python in 115. Those are both interpreted languages, which means your code is executed one line at a time. A lot of hard content got cut out. The JSON wasn't even hard content. It was just a distraction. It was a one-off topic that really didn't fit its purpose. I was trying to use that to reinforce inheritance and polymorphism, and it just wasn't doing that the way I wanted it to. So I'm using that lecture time on other things that I think will be more beneficial to you. I'm not just cutting hard content. I'm rearranging the content to reinforce the concepts that I need you to understand. JSON really isn't a concept that I need you to understand. You already know what JSON is. But the JSON lecture was supposed to reinforce the OOP content. Anyway, interpretation, if you're watching on YouTube, sorry. The interpretation, your code is executed one line at a time. The interpreter reads the first line of your code, executes it, moves on to the next line of your code, executes it, and actually reads your code when your code is interpreted. As opposed to compilation. With compilation, first your entire code for your entire program is translated into another language by the compiler, and then that language that you translated into, that the compiler translated into, that code is interpreted. So we have 2 steps in our process of running a program. And you notice when you're in IntelliJ and you click run this program, you notice there's quite a delay and there's a progress bar in the bottom of your screen. There's quite a lot going on. That's not because IntelliJ's slower or anything like that. It's because we're using a compiled language instead of an interpreted language. You can run Python in IntelliJ and it'll run right away. Once you click go, it just starts running, just like your code did last semester in even in an online IDE. But now we have a compiled language. So the compiler has to look at your entire code. And if you're, say, running the examples repo, it has to compile that entire project, every example in there, translate it all into another language, and then run that other language. Where with an interpreted language, you hit go, and it goes right to your first line of code and starts running it. There's no middle step to be done. So Scala is a compiled language. So we have that extra compilation step. A few things one big thing that I want to point out, Java bytecode is, and we'll talk about that in a second. With interpreted code, you're more likely to have runtime errors. With a compiled language, you're more likely to have compiler errors. So you're going to see more compiler errors, which at first may look the same as runtime errors if you're not really watching, but there are important differences. And you'll tend to learn to love compiler errors because it's looking for any errors in your program and letting you know right away before it even tries to run your program. It'll say, hey, there's an error. You really got to fix this before I run. With a interpreted language, the program's going to run, and then when it runs into an error, if an error is executed, then it's going to crash. And you're going to have more programs crashing, which generates a lot more really horrible bugs for your end users, as opposed to compilation errors where you compile it, the compiler says, yo, something's wrong, you fix it, and then nobody ever sees that error because you fix it during your development process. So here are two examples of a Python program that's going to run. One has an error and one doesn't. So this one, we're going to run this program, and this is a quick example of a class. I moved the content where I introduce classes. I actually do it after this lecture. So we haven't even talked about classes in Scala yet. But this is a Python class. We're going to create an instance of this class called an object. That doesn't make sense. Don't you worry. You're going to get plenty of classes and objects in your life next week. But we're going to create this, set this state variable to some initial state, which is 5 in this case, the number 5 as an int. And then we're going to call this add to state method, which is going to add 10 to that initial 5 that we gave it. We're going to print to the screen, just say, hey, we're adding this number, and then we're going to add that number to the state. So we're going to start with the value 5, we're going to add 10 to it, then we're going to print out object.state. This is going to print adding to state, and then it's going to print 15. Everything runs fine, no errors here, nothing wrong. We're going to have the same program over here, except we're going to have in quotes a string 10 instead of the number 10. Now the program runs. Since this is interpreted, it's going to start at the start of our program, the start of our main method, run this line, which runs this line, then runs this line. It's going to print adding to state. That will be printed out. Your program will run and get to this line. Once it gets to this line, and it's self.state, which is the number 5 as an int, plus equals to add, which is 10, the string, we can't add a string and an int together. So at this point, your program's going to crash. Python's going to say, I can't add an int and a string. What are you doing? Program crashes, incompatible types, and nothing runs after that. So we never get to print this statement, but we do get this far. An interpreted language is going to run until it crashes. As opposed to the same example in Scala, in this is going to run exactly the same, running the same code, but in Scala, we start with 5 and we try to add 5 and 10. Everything runs fine. This compiles, this runs. Everything's fine, prints out adding to state, prints out 15. If we change this from the int 10 to the string 10, now this program will not run at all. It will not do anything. The compiler is going to look at this code. It's going to try to translate it into another language. And it's going to get to this part right here. It's going to, actually this right here, it's going to say, hey, add to state, you're giving me a string, but you told me that that method takes an int. This is not an int. Fix this problem, because with that issue, I don't know how to convert this into another language. I don't know what to do with this. So since that is the wrong type, the compiler, before your code ever runs, is going to tell you have an issue. So this code will not run. It will never be compiled, and you'll get a compiler error of incompatible types. Expected int got a string. So it never compiles. This never gets printed. This never crashes. This line actually does not give you an error. It's going to be this line right here that gives you an error for that. Repetition, I feel for you. That's a rough one. So a compiler is going to look for those issues before running your code, while it's converting your code into that other language. And the compiler does a lot for us. Compilers these days, modern compilers, are really fascinating pieces of software. They find a lot of optimizations for us. They really streamline our code. They let us be worse programmers and then fix our code to make it more efficient as it's translating into another language, on top of looking for our errors and notifying us of the errors that we've written. Compilers really help us out a lot. It's something we don't get with interpreted languages. Scala compiles to Java bytecode. So Java bytecode is the actual code that we run. And Java bytecode runs on the JVM, which if you've ever seen these pop-ups, which I'm sure you have, update your Java, Java's out of date, we have a new version for you. That's Java, which is the Java virtual machine, which is the software that interprets Java bytecode. This is the same code that, of course, Java code compiles to. Java compiles to Java bytecode. Scala compiles to Java bytecode. So if you have a Java program or a Scala program, after it's compiled, those two programs are effectively the same. They both run on the JVM. They can be ran anywhere that either of them can run. And we can actually mix Java and Scala code. We'll see it later on in the course. We'll actually use Java libraries in our Scala code. And since they both compile the Java bytecode, we can use them interchangeably. If you have a big Java program, you can throw some Java classes in there. You can write a Java class, and it'll work alongside all of your Java code in your Java project. Because they both compile to the same language. This Java bytecode, which runs in the JVM, which is Java, installed on 8 billion devices or whatever they're up to now. That Java, that's where your Scala code is running. That's why we had to download the JDK, so we needed all those Java tools, because we're working with Java bytecode. Oh, I already said all this. And like we saw, when you use capital M math, that's actually a Java library, or that we're using Java code already in our programs. We saw that Scala's string class is actually just the Java string class. The developers of Scala didn't bother writing their own string class. They just used Java string class. So you see that in the language itself, Scala isn't a whole language all completely built from scratch. They borrow from Java a decent amount. Because why reinvent things? All right. Any questions on that? Quick before we start talking about memory. How much of Java will I know if I get Scala down? In my opinion, like most of it. I think knowing Scala and then trying to pick up Java after that should not be difficult at all. You have to get used to the Java syntax. There are just a few different things. Like the return type goes before the method name in Java instead of after, like in Scala. Things like that you'll have to get used to. But since they both compile down to Java bytecode, they both just inherently have a lot of similarities to them. They're very similar languages. So once you know how Scala works, you really know how Java works as well, and it's just a matter of some syntax. Which, not to take that lightly, some syntax can take you a while to get, but nothing like learning Scala coming from JavaScript and Python. That's a big jump, and that's why we give that a lot of attention. Scala to Java, I think you can pick up Java after this pretty easily. What do self and this do? That's something I'll save that for next week. I'll give a very quick explanation, but it accesses the variables that are part of that object. But we'll talk about that at length next Monday, I believe, is the first time I introduce this. And then self in Python is the same as this in Scala. They have the same effect, just different syntax. Will we ever use Java later on? I don't think any courses in our curriculum require Java anymore. So you'd have to pick it up on your own if you want to use Java. Yeah, and if you get a job and they're a Java shop and you're like, hey, I really like Scala syntax, you can start pitching it to the team and just start using Scala alongside their Java project. And start converting them over to Scala, over to the good side. To get an A after a recovery plan, definitely possible. If you get put on a recovery plan, you can still get an A. You can still catch up. I mean, I expect a decent number of students to get put on a recovery plan just for missing one requirement. Maybe you got sick and missed the first interview and quiz, and then you had to rely on the second chance, and maybe your interview just didn't go as great as you expected. And you just have to go on a recovery plan to make up that interview or something. Like, you can get put on a recovery plan for not really being behind, and that's okay. And you can still recover and get an A. All right, so let's move on to some memory. Yeah, I like Scala better than Java. I didn't think I would, but once I started using Scala a bit, I was converted over to the Scala side. Now I preach Scala. Scala just has a lot nicer syntax once you get used to it. It cuts down a lot of the redundancy. Java makes you repeat yourself a lot. And Scala says, nah, I got you. Like, you don't have to tell me. I heard you the first time. All right, so let's talk about memory. So when I say memory, I mean RAM. If you've ever built your own computer or cracked open your computer at any point and you've seen these RAM sticks, this is what we're talking about. Whenever we talk about memory, we'll talk about stack memory today. Next week, we'll talk about heap memory. It's all on your RAM stick. So this RAM stick has this memory, and we want to use that to store all the values of our program. And this is where everything with our programs is going to be stored until we have some file I/O and we're accessing the hard drive. So RAM is much, much faster than disk space. If we ever have to save to disk, even if it's an SSD, a solid state hard drive, the RAM is much more efficient. It's much faster than the hard drive, which also makes it much more expensive. If you want to buy 16 gigs of RAM, that's going to be pretty expensive. It's going to be roughly as expensive. Somebody will call me out if my numbers or my estimates are off, but roughly as expensive as a terabyte of hard drive. Much more expensive. You're paying for that speed of being able to access that memory very, very quickly. Yeah, don't download RAM. RAM is physical. It is a physical thing. You can't download more RAM. Don't fall for that one. But it's a funny joke if you try to trick someone else. Can't download more RAM. So when we run our program, we're going to ask our OS, or rather the JVM is going to ask our OS for a chunk of memory. And then the JVM is going to give that chunk of memory to us. I'll cut out the JVM in my explanations just to save words, but I'll say we're going to ask our OS for memory and get some memory. So when we run our program, we get a small chunk of that RAM stick for us to use for our purposes. So when we run our program, we get this memory, and we can do whatever we want with that memory space. We have and RAM is indexed. We call it random access memory. It's like one giant array. So we have to use this array of data, array of storage, and make use of that how we will. So this memory, this chunk of memory that we get for our program, is going to be used for a couple of different things. On the very bottom of this, what we'll call the memory stack, is going to be various program data. This is like metadata about our program. This is something that will be more important. I believe in 220 you'll talk about this in quite a bit of depth. For this class, we're going to ignore this. But if you look at the documentation, one of the links that I give on the schedule for this lecture, it will talk more in depth about this if you want some good information about that extra program data. We're going to ignore it for 116 purposes, and we're going to start at the top of the stack. On the top of the stack, when we run our program, will be any command line arguments that we'll use, which again, actually, I don't think we use command line arguments either. And then the rest of this memory is going to be the stack memory for our program. This is the memory where we're going to store all our variables, where we're going to put all our method calls. This is where we get to work. This is our working space, kind of our scratch paper for our program. The stack, the memory stack that we're going to talk about, which is going to go in that chunk of memory that we just saw, is going to be a last in, first out data structure. So we can only add values to the bottom of this stack, and the stack grows down. So we can fill this memory slot, then this memory slot, then this memory slot. We can remove only the bottom memory slot. So this is like a stack that's growing upside down. We always draw upside down like this because that's how it's actually being stored in RAM space. Are stack memory and memory stack different? No. I might use those interchangeably from time to time. Whenever I say stack, I mean the same thing. Until we talk about the stack data structure, but that's not till learning objective 4. So whenever I say stack memory, I mean the same thing. So this is a last in, first out data structure. We can only add to the end, and we can only remove from the end. And we can't access the variables that are too far up the stack. Well, we'll talk about that. Ooh, that is where Stack Overflow comes from. Wednesday we'll talk about Stack Overflow. So a few things about the stack. What's up, Trino? Every time we call a new method or a function, we'll talk about way later. Every time we call a new method, that method call goes on the stack in a new stack frame. So we're going to create a stack frame for that method call, which is effectively an isolated environment that cannot escape that frame. So everything that happens within a method call is strictly within that stack frame, and anything outside of that stack frame cannot be accessed. So anything happening elsewhere in your program, it kind of gets pushed off to the side until this stack frame for this method call is gone. Once the method call ends, that stack frame is destroyed. Anything that was part of that method call is destroyed, and then its return value goes back onto the stack to whatever method was calling it. Similar to stack frames, we also have code blocks which create variable scoping differences. So every time we enter a new code block, which is an open brace, we're going to create that block in the stack. And this is similar to a stack frame, except we can escape and read values outside of that code block. But any duplicate variable names are going to be looked for inside of that block before searching outside of that block, and we'll never search outside of the stack frame. So, and any variables that were declared inside of a code block, once you hit the end of that block, those variables are going to be destroyed. So this is a common, Alive, don't worry, I will go through an example of this. I want to get all the explanation out front, and then we're going to go through an example and explain what all this means. So any variable, and this is a common 115 error, say you have a for loop, and you have a variable, or rather a conditional, you have an if, and you're creating a variable inside the if statement, and you want to return that after the if statement's over, you want to return that variable. That's something you can't do because as soon as you hit the end of the if block, the variable that was declared inside of that conditional is going to be destroyed. The end is the closing brace. So once you hit the end of that block, all the variables declared inside of that block are destroyed. All right, so what the hell does all that mean? That's a lot of information, so let's dissect this. Let's break it down. The rest of the lecture is going through this example and explaining everything that we just heard. So we're going to look at this example and trace through the execution of a program and watch the values on the stack, watch the stack frames get created, and look at the code blocks as they create variables and destroy variables. This example is intentionally language independent, though it does, just by pure chance, I happen to write it as valid JavaScript. I should have a let I here and to declare my variables. So these would all be global variables, but this would actually run as a JavaScript program. But that was purely coincidental. This is meant to be language independent, so we can focus on the concept of stack memory instead of being hung up on the syntax of any particular language. So let's talk about stack memory as it pertains to this example. So the very first thing we do, we are starting our program. We're going to start with the main method, function in this case. I'll probably end up calling them methods throughout this example just by habit since we've been talking about methods. We're going to start with the main method. The main method always takes your command line arguments. So this program's going to start. We're going to ask our operating system for a chunk of RAM that's going to be used for our stack space, and we have to work within the confines of that chunk of RAM that our operating system gave us. If we go to the memory address before that chunk of RAM that it gave us, that might be used by another program, and our operating system should yell at us and say, you're not allowed to use that. Or at the very least, the JVM should yell at us and say, look, you can't access that part of memory. And right after the last byte of memory that the operating system gave us, that might also be used by another program. It might not be, but it might be enough so that we're not allowed to access it. We don't have permission to access that chunk of memory. So we have to work within the confines of the stack that we have in the memory space that the operating system gave us. And a quick foreshadow, we'll talk about it on Wednesday. But if you run out of space, if you use up all this space and you try to use one more byte, that's your stack overflow. It's going to crash your program and nothing works after that. You don't want to overflow the stack. Luckily, we get tons of stack memory for our programs. Overflowing the stack is not something you have to actively think about unless you do something horribly wrong. If you do something horribly wrong where your program is going to effectively ask for infinite stack space, that's when you're going to overflow the stack. But for normal working conditions, you're not going to overflow the stack. It's not something you need to be concerned with. I drew this fairly small so it fits on a slide, but you'll have tons of stack space, tons to work with. So, all right, we get our stack space from the operating system. We have the memory addresses that we get to work with. We're going to call our main method, and the first thing we get are these command line arguments. This is if you're calling your program from a terminal and you give it some command line arguments, which I'm not sure if there's a good example that you'd all be aware of at this point. But if you run your program with command line arguments, not something we'll use in this course, but that'll be the very first thing that's on the stack, those command line arguments. In Scala, this is args, that array of strings that you have to have as an parameter to your main method. These would go on the stack first thing, very first thing. All right, so let's go through this line by line. Next thing we're going to do is declare a variable named I and assign it the value 5. So whenever we declare a new variable, that variable is going to go on the stack. It's going to take up the next available piece of memory, and that's where that value is going to be stored. So we're creating a variable named I, assigning it the value 5, and that's staying on the stack. That's going to stay on the stack right there until it's destroyed, I guess. The type's not listed, so this is a language independent example, so we're not bogged down and distracted by types and things like that. I just want to get the concept. I want this to focus on the concept of a stack without thinking about anything else. So this is language independent. This isn't Scala code, but I'm going to create a variable I, set the value 5, and that goes on the stack, on the next available space every time we create a variable. Next, we're going to move on to the next line. And when we have an assignment, the way the program executes is the right-hand side of the assignment is always evaluated first before the left-hand side, before this actual assignment is executed. So the very first thing we do when we get to this line, we start at the right side and evaluate this down to a single value before we create the variable n. So the variable named n does not go on the stack yet until compute factorial returns. Once that returns, we're going to create a variable named n and put that on the stack. Oh yeah, definitely. The quiz and interview are a lot about stack memory. So we're going to call this method. Whenever we have a method call, we create a stack frame. A stack frame is an isolated environment that can only access the stack memory within that frame. So once we get to this compute factorial call, we're going to create a brand new stack frame. We're going to create the parameter variables, this case just one, n. We're going to create that parameter variable, put that on the stack, and assign it the value of the argument, in this case I. So what's I? JVM's going to say what's I? It's not going to look up here at our code, but it's going to look over in the stack. It's going to look on the stack and say, do I have access to a variable named I on the stack? It's going to say, I sure do. It's going to find it right here. And it's going to say, oh, I is on the stack. It's currently storing the value 5. So the argument resolves to 5. And we assign that to the parameter n. And put that on the stack. That's the first thing that goes on the stack in a new stack frame are the parameters assigned to the arguments. So now that we have n on the stack, in this new stack frame, now we can start computing on our method, create a variable named result with value, assign it value 1, put that on the stack inside this stack frame. We get to this loop, and now we begin a new block. We create a new block. We create a variable I, assign it the value 1. Inside of that block, because we hit an open brace. Whenever we hit an open brace, that's the start of a block. Whenever we hit a closed brace, that's the end of a block. The same is actually true for method calls. We have this block, except method calls are a little bit special. They get elevated to a stack frame instead of just a code block, but they are also a code block. So we create this variable I inside the code block with value 1. And then we iterate over this loop. We're going to check the conditional. Is I less than or equal to n? And now we have our first check of a variable name that's not in the current scope. So we have a check. I less than or equal to n. We have to resolve I and n to values. We have to resolve both of these expressions to values so we can execute this comparison. We're going to start looking inside the current scope that we're in. We're inside this code, this loop block right now. We're going to look for a value I, a variable named I. We find it right here. It's storing value 1. So this resolves to a value 1. Next, we look for n. We look for it inside this loop block. Well, inside this block, there was no variable n that was declared. So there's no variable n that exists in this block. So we start expanding our search and we look outside of that block for a variable named n. So we look in the whole stack frame in this case. We look at the next level up. Here we do find a value n. It has a value 5. So this is going to result to 5 because that's where we checked. That's where we found a variable named n. Since 1 is less than 5, we're going to execute the loop body. And we're going to look for a variable named result. Now, same thing. We're going to start inside the loop block. We're going to not find a result. We're going to look outside the loop block. We're going to find a result, value 1. We're going to multiply that by I. Okay, so now we have to resolve I to a value. We're going to look inside the loop block. We find a variable named I, storing value 1. So we multiply result 1 by I, 1, and then store that back in result. Again, result we don't find inside the loop block. We do find it here, though. And we do notice that we can have multiple variables of the same name. So right here, I have a variable named I inside this loop block. I also have a variable named I here in the main block, the main stack frame. But since this is outside of my current stack frame, I can't even see that variable I. That's out of scope. I can't currently see it. But this variable I, we can see. It's in scope. So we do see that one. There could also be another I out here. But if we're inside this loop block, we're going to see this variable I before we look outside the stack frame. So we can, and on your quiz you will, have variables with the same names, and you have to pay attention to which one is going to be seen based on which stack frame you're currently working in and which code block you're currently working in. So in this case, we found this I, this result, and did our computation on this line. And then we loop for a while. We know what loops are. We hit the, somebody did ask what I++ is. So when we hit the end of the loop with this syntax, which you may have seen in JavaScript, but with this syntax, we hit the end of the loop, and we're going to run this this expression, I++, which is going to add 1 to I. So I, we find it inside the loop block, add 1 to it, and we get to 2. We're going to keep running through this. We get to the top again. We check our conditional again. It's still true. We run the code again. We increment I again, and we keep doing that until I is 5. We're going to run the loop one more time, actually. I should have... Oh, yeah, so I is 5, and then we're going to increment I once. It's going to be 6. We're going to check the conditional. It'll be false, so our loop is going to end. And we're going to go to the end of this execution. So we've hit the end of that. Oh, let me go right here. So we've hit the end of our loop block. We've hit the closing brace. Once we hit the closing brace, any variables that were declared inside that block of code are going to be destroyed. In our case here, that's I was the only variable declared as part of this loop. And any loop variables like this, even a for each loop for variable in data structure, that variable is going to be destroyed at the end of that loop. You won't have access to that after the loop is executed. So we hit the closing brace. The entire block is destroyed. So we're going to pop values off the stack until we reach the beginning of that block. Once we hit the beginning of that block, we're done destroying things. And it's like that loop never existed. So after the loop, or after any code block is done, the only effect that has is any effect that it had on variables outside of that block. So in this loop, we modified result. Each time we kept multiplying that by I. So since we kept multiplying that by I, we can see that effect of the loop. So the loop had the effect of modifying result. But anything that was part of that loop, any variables declared in that loop, are gone. We can't access I anymore because that was declared inside that code block. So now result is 120, and we're going to return result. Once we hit a return, or in Scala, we hit the end of the method block. The entire stack frame is destroyed. The entire stack frame, after a method call executes, the entire stack frame is completely gone, and whatever we return, that's what the method call resolves to. So we return this value, we end the method call, stack frame is completely destroyed, no memory of it exists anymore. We remove that from that bottom of the stack or top, depending on how you want to visualize that. And compute factorial of I is returning this value 120. So this expression resolves to this value, and that's the only artifact that we have of that method call, is this returned 120. The result is gone, I is gone, n is gone, all those variables are gone. They don't exist anymore. We return, and now that we're back in our main method, we can finally create this variable n in the main method, which again, we can reuse variable names as long as they're not in conflicting scope, as long as we're paying attention to where each variable is accessible from. We can create this in this stack frame, the main method stack frame, create that variable n, assign it the return of this stack frame, which was 120, and then we can just print n to the screen. We're not doing anything fun here. We just print n to the screen. So we print n, prints 120. We look for n, 120. Done. Once we hit the end of our main method block, all of the memory is freed up. We go back to the OS and say, hey, we're done with that chunk of that RAM stick. You can have it back. You can give it to the next program, the next process that's going to ask for memory. But we're done with it. And there's no memory at all. Our program's gone. No memory of it exists. Unless you did any file I/O, there's no memory of your program. No memory left. So what you're supposed to write for the stack, in general, you're supposed to write, human beings are going to read these and assess them. So if you write something that shows that you understand the stack, then you're good for that question. So when I say explain what happens throughout the execution of this program, you should pretty much go through what we just did in lecture. Okay, this gets put on the stack, then a new stack frame is created. We just entered a new code block, so that happens. And when I ask, write the state of the stack at a particular line, a particular highlighted line, I would want to see something like this, or at least the best you can, given that you're filling it out in a Google Sheet as a paragraph answer. If you fill it out like this, if you give me this and then a few blank lines and then an explanation, that'll be perfect. That's a top-notch answer. And in general, for the explain what happens in memory throughout the execution of this program, for those questions, the more detail you can give, the better. Don't leave it up to us to guess if you understand what you're talking about. And you have 110 minutes. You have quite a bit of time to write this stuff. The more detail, the better. Don't leave it up to chance. Don't leave it up to us just assuming that you know what you're talking about because you didn't feel like writing it or anything. Just give as much detail as you can. If you can give as much detail as I just did going through this, you know you're going to be fine. If you give less, you're playing with fire. You might not get your credit. You don't have to use exact wording. So that's what I mean. Like a human being's going to read this. As long as we can understand what you're saying, then it's fine. You don't have to use the exact wording, the exact terminology. Like stack frame, you should use that terminology because that's fundamentally part of this. Code block, you should use that terminology. Stack and memory address, you should use that. But it doesn't have to be exactly the way I said it here. However you understand it and however you can explain it. As though you were explaining to somebody else who doesn't understand the stack. That's what you should do on your quiz. Somebody who doesn't understand stack memory but has a good programming background, how would you explain what's happening in the stack to them? How many quiz questions? I'm not positive yet. Probably 3 or 4, though. Why even write it if it's going to be destroyed? All right. This slide will make more sense when we start talking about the memory heap, but I still want to talk about this right now. Anything that's a primitive, that term is only going to make sense to people who know Java, but these are going to compile down to primitive types in Java bytecode. Double float, int, long, short, char, byte, and boolean. These values get stored on the stack directly. So for the quiz on Thursday, you're only going to see these values because we haven't seen anything other than these values, or rather we haven't talked about how they're stored in memory. So like array, map, you're not going to see those on the quiz because we haven't talked about how they're stored, because they are stored in a different way using the memory heap or heap memory. Yes, I use those interchangeably too, which we won't talk about until learning objective 2. So worry about these and how they go on the stack for now. And we get, oh yeah, now all others are in heap memory, which is something we're not thinking about quite yet.